Before we leave recursion on lists, I'd like to talk about some other forms of recursion. We might have a different base case. We might, for example, not start with an empty list. We might want to work over multiple lists, or we might want to combine list and number recursion. In general, we might write recursions which look at smaller lists, but not just looking at the tail. And then finally, we'll do something called tail recursion, which is a different style of recursion altogether. We'll look at two ways of defining the reverse function. And then that will be the end of our overview of recursion on lists. Now, if we want to take the minimum of a list of integers, the problem we have with the standard template is that we worry about what the minimum of an empty list is. Is it 0? Is it minus infinity? Is it plus infinity? So it's better to leave that undefined and say, let's start the recursion with a single element list and say the minimum of singleton list with x in it is x itself. And then we have to think, well, what's the general case where we have x consed onto a list x's, which we assume is non-empty. So what's the minimum going to be there? Well, either x is going to be the minimum, or it's going to be inside x's, in which case it'll be the minimum of x's. So what we do is we take the minimum of those two. We take the minimum of x and the minimum we've already calculated of x's, and that gives us our definition. So it's like the standard template, except we started off, so it's only defined over non-empty lists, and we started off at a singleton list rather than at an empty list. A second form of recursion is zip, which we've met already. Here's you can see at the top there's an example. If we zip together those two lists, which are of different length, the first is of length 2, the second of length 3, what we finish up with is a list of length 2 containing the pair 3, 3, that's the first element of the two lists, and the pair 1, 2, which are the second elements of the two lists. Now, because one list only has two elements, we can't go any further. And so at that point we stop. And that's what you see reflected in the definition. It says, if there is an element in both of the lists, we take that front element off each of them and turn it into a pair, and then put that on the front of the result of zipping the remainder of the lists. But if we have either of the lists being empty, which is what we cover by this second case here, we only hit the second case if the first pattern match fails, that is, at least one of the lists is not non-empty, that is, at least one of them is empty, we return the empty list. And that has the result of behaving as we specified in the case where the lists are not of the same length. Namely, we drop the elements which are unmatched, so we drop the remaining elements of the longer list. What about a function that takes a number of elements from the front of the list? So for example, if we take two elements from the list 3, 1, 3, 2, 5, we get the list 3, 1. Now here you can see we're kind of combining recursion over the list and recursion over the elements. Let's have a look at how that works. The first clause says if we're asked to take 0, then we take 0. We return the empty list. So in the first clause, we're told to take nothing, so we take nothing. In the second clause, there is nothing to take. So again, we return the empty list. And only in the final case do we take the element x off the front of the list and cons that on taking n-1 elements from the remainder of the list. So we're doing recursion simultaneously on the number and the list here. We both take one off the number and we take one element off the list, because we're going down in lockstep until we hit 0. So the way this works is if we asked to take 10 from the list 1, 3, 2, 5, we would get the whole list. So it takes as many as it can from the specified number. But if we hit the second clause, we will return an empty list because there's nothing else to return. And finally, we have what I think is a lovely algorithm for what's called quicksort. Quicksort takes a list of integers, or a list of anything that we can sort, in fact, and returns that list sorted in ascending order. What does quicksort do? It says, first of all, on an empty list, we return an empty list. And then, if the list is non-empty, if its first element is x and the remainder is x's, we do the following. We select the elements from the list that are no bigger than x and sort them. Then we have the element x, and then we sort the elements from the list that are actually bigger than x. And you can see that this will result in what we would expect. Well, I say you can see. Let's take a look at that now and see how it works out in practice. Let's look at quicksort. We'll write QS of 4, 1, 7, 3, 8, 9, 2, 6. What's that going to lead to calls of? On the left, it's going to give a call. We're going to run through x's, which is this part of the list, and we're going to select the elements which are less than or equal to 4. So it's going to be quicksort of 1, 3, 2. And on the other side, we're going to run through x's and find the things that are bigger than 4. So it's quicksort of 7, 8, 9, and 6. So you can see what this does precisely is ask us to do a quicksort of the things no bigger than 4 and the things greater than 4. So while we're calling this not on a sub list, not just on the tail, but we're selecting certain elements, but when we're doing that, we're doing it only for lists that are no longer than the original list. We're doing it, in fact, for lists that are shorter than the original list. So you can see here that eventually, if we keep doing this algorithm, if we do it again here, we'll call quicksort on the empty list and quicksort on 3, 2, because we divide at 1. And you can see that we will eventually come to a point where the quicksort will terminate, because we will hit empty lists. What we're going to conclude with is looking at how to reverse a list. And what I'm starting with is a direct definition of reverse. The function rev takes a list of any type and returns a list of that same type. What does the definition say? It reads just like a description of the reverse of a list. It says the reverse of an empty list is the empty list, and the reverse of a non-empty list is got by reversing the tail and then sticking the head at the far end. We do that by putting the head in a list on its own and joining those two together. But because of the way we're using concatenation here, it's inefficient in practice. So if you try evaluating rev of the list 1 up to 100,000, you will see that its evaluation is slow, and you'll need to interrupt it with Control-C. And that's because this algorithm is quadratic in the length of the input list. So let's look at a way of writing a definition which is much more efficient. We do this by writing this tail recursive definition, and I'll explain in a second why it's tail recursive, but we get reverse of x's by shunting x's and the empty list. And what does shunt do? Shunt is called that to it's reminiscent of the way that railroad cars get shunted in a shunting yard, if you're familiar with that. So what does shunt do? If the first list is empty, you return the second list. Otherwise, if the first list is non-empty, you take the first element off that list and put it on the front of the second list and call shunt again. So this is a recipe for working out the reverse of the list, but it doesn't describe it in the same way. It's a recipe of steps you can take to reverse the list, but it's harder to understand directly what it will do. And it's called a tail recursive function because the recursive case, the last thing, in fact the only thing here that it does, is to call itself again. But the result of this is that the algorithm is linear in the length of a list, so it is efficient. Let's take a look and just see how it works in practice. Here's the definition of shunt, and let's just try it on a small list. What is shunt of 2, 1, 3 and the empty list? Well, we take the first element off the first list and put it on the front of the second and continue. And you can see that what this does indeed is return the list 312, which is the reverse of the element of the list that we put into the first argument. And so that does efficiently provide us with the reverse of a list. Now it's quite uncanny what's going on here. We've got the shunt function here. It's possible to look at the two arguments of shunt as being two storage locations. And if you look at what's happening in the second clause here, we take, before the case is that we have x colon x's and y's, and in the after case we've got x's and x colon y's. So it's almost as though we're updating those positions, and we repeatedly update those positions until we hit a point where the first element is empty. And you can read that as this loop. While x's is not 0, do this simultaneous assignment. Simultaneously replace x's with the tail of x's and y's with the same list with the head of x's appended to the front. And if you continue to do this, it will, until x is 0, put the elements from x's on the front of y's. If we start with an empty list there, we'll finish up with the reverse of x in the variable y's. So this tail recursion in Haskell or in any other functional language behaves like a program with updatable variables in a traditional programming language. So if you like writing programs in that style, here's how you do it. But I would argue very much that it's harder to understand directly what this does than it is to understand the direct definition, even though the direct definition is way less efficient. This is linear, the direct definition is quadratic. So tail recursion gives us this way of simulating updatable variables. It gives us that way of programming by changing the state of a machine, if you like, rather than computing the value of a function. But it is then less clear how a program behaves. So there's a trade-off there. There's efficiency for comprehensibility.